Hello from wherever you are. This is Bill Lydon, editor of Automation.com. Today we are going to revisit the idea of using PCs as a control element in industrial control systems. We've titled this Revisiting the PC versus PLC Debate for Control Systems. It's widely accepted that applying computing at plant processes and machines is improving industrial efficiency, flexibility, and visibility, with more powerful PLCs and process controls being used to accomplish this. In a number of cases, more power is being added with a PC embedded in a proprietary PLC module that slides into the PLC rack. But the latest addition to the industry is called the PAC, the Programmable Automation Controller, that are much more powerful controllers. The term PAC continues to be imprecise since there is no industry standard to use as a benchmark. The PACs combine the features and capabilities of PC-based control systems with those of traditional PLCs. But overall, the goal of leveraging computing to make production more efficient is our objective to accomplish increased productivity. One of the questions that's been reoccurring over the years is, should PCs, characterized sometimes as x86-based computers, be used as the primary control? There was a movement in the 1990s to do that, but it really wasn't successful, and I'm very familiar with that, at the time being a co-founder of a quote, soft control company. But a lot has changed in technology and manufacturing since that time, so we're revisiting this issue. We discussed this with Dell's people from Dell Corporation, Josh Neland and Tim Alteri. Tim, by the way, has a deep background in industrial automation and manufacturing, and we really started a debate between the two of them of the pros and cons of using PC technology in manufacturing. Let me introduce Josh and Tim. Josh handles OEM marketing at Dell for workstations, desktops, and portable-based solutions. And over the past 8 years at Dell, he has participated in consumer product line marketing, supply chain management, quality improvement, firmware development, and factory infrastructure. Before joining Dell, Josh worked for various startups, including Trilogy, where he developed configuration solutions for the automotive industry. Tim is a chief client executive at Dell's Industrial Services Group, providing technology consulting to Dell's manufacturing clients, and has served as CIO for international outsourced clients. But Tim has a broad background in manufacturing. Prior to joining Dell, Tim served as Director of Operations and Engineering in heavy manufacturing and Tier 1 automotive suppliers, where he ran plant operations, led controls engineering teams. In these roles, he led automation and process innovation, including patented designs for high-speed closed-loop testing and process adjustment systems. Tim has a 26-year career in manufacturing, 13 of which were in operations and plant management. So that kind of sets the stage. This is meant to be a thought-provoking session, and we expect it will bring about a number of questions and comments. So we'd encourage you to use the question widget you should see on your screen to submit questions and comments. We may not be able to handle all of the questions and comments during the webinar, but we will follow up on those that are not handled directly in the webinar. Josh is going to start by introducing himself, saying hello, and then Tim will start the debate or discussion about the PC versus PLC. So, Josh, I invite you to kind of say hello and get things rolling.
Well, thank you very much for having me, Bob. I look forward to the webinar. So with that, I will hand it over to Tim.
Okay, I'd like to kick off the discussion by using a real-world example, and hopefully this will provoke all of the elements of thought that we wanted to include in the webinar. So here's a real-world example. I still look at everything from a plant manager viewpoint because having grown up in the plant and spent most of my career there, that's still how I view things. This subject matter is near and dear to my heart. So a real-world example, I have a manufacturing line in Romania. I had moved it there because the low-cost labor in Romania was attractive. Well, the labor differential and the transportation differential has changed over time, and so now I want to move that production line to one of my facilities in Mexico. So at a high level, we look at the shipping costs of moving the line, we look at the labor differentials, we look at the productivity differentials, we look at any shipping and logistics issues for getting the supply chain redirected into Mexico and then out of Mexico to our customers. We get all that arranged. Those are the things that at a management level we're worried about, and we model. We make the decision to go ahead and move the line. We move the line, we go to bring it up in Mexico, and we find that the control infrastructure in Mexico uses all Siemens PLCs and handheld Datamite style, very old, handheld Datamite style data collection for the product genealogy. While it was in Romania, we had actually done a greenfield in Romania, and we had brought the lines up originally with completely PC-based controls. We had some PLC controllers, Allen Bradley, on the lines to actually do the actuation, but all of the measurement of the process parameters and the alignment of those process parameters and recording of them with the product genealogy into the ERP database was done completely by PC control. Now, at a high management level, we had not delved into that level of detail, so we moved the lines, and suddenly my operations plan to bring this online and start shipping to the customer is delayed by more than 3 months because the process engineering group and the IT group tell us that they have to completely redesign the control parameters. So then we step back and say, well, let's not have that time delay because we had already made our commitments to the customers. Let's just pick up the PCs that we had in Romania, move them down to Mexico, and hook them up and get going. Well, then they tell us, well, the actual software that we had used to develop the interface between the PCs and the PLCs in Romania is licensed to our legal enterprise in Romania. And we don't have the licensing schema for that in Mexico. So we're going to have to buy those licenses all over again for our legal enterprise in Mexico. So now we have additional outlay of money. We have to decide, well, do we redesign it from the PLC bottom up in Mexico again, or do we transfer these computers? Well, can't transfer the computers either because the importation and exportation of that kind of technology is regulated. And so we can't just pick up the computers and move them. So let's just buy new computers. We'll buy the enterprise license for Mexico. We'll buy new computers in Mexico, and we'll just hook it up. Okay, let's do that. We go to buy the new computers, and what's available on the market today is what's available. However, the computers that we had in Romania were actually older computers, and they had 3 ISA slots in each computer. And in those ISA slots, we had the data capture cards, which were $3,000 each, that we had designed the whole system around. And we can't buy computers with 3 ISA slots anymore. And we can't just go buy new data capture cards because then we would have to recalibrate and recertify with the customer the data capture analysis to make sure that the customer has the comfort level that the data capture and the engineering algorithms between the calculation of the data capture of the raw voltage calculations, transposing that into torque and the other calculations that go into the product genealogy, pass their certifications. The whole thing becomes a mess. So there's my short anecdote, which describes all of the real-world problems that we face day to day. This was a problem in 2010, and how we solved it is still ongoing, but I think it brings to light all the different things we want to talk about here today.
Very interesting.
Well, over to you, Josh.
Well, actually, let me ask you to elaborate a little bit. So the first time we talked, you told me a little bit with anecdotes like that one about how the industry has changed, how manufacturing has begun changing because of various forces like the ones you're talking about. Can you elaborate a little bit more on the systemic forces that you're seeing?
Yes, in fact, when I first started in manufacturing, everything was run on PLCs. We had the Belkin blue cable dropping down to the PLCs, and we had things like some of the third-party softwares that were designable to do process data collection at first and then interface with the process itself to make adjustments based upon the data collection that they were doing. That movement, as was stated at the beginning of the webinar, that movement continued for about 10 years. And we got deeper and deeper and deeper into the actual x86 architecture taking control of the processes. And that really gave rise to two significant problems. The biggest problem, by far, the overshadowing problem, was that manufacturing needs to be able to operate by direct labor. And when you move all of the intelligence of the process into the x86 architecture, then you're taking it out of direct labor in most settings. Most countries in the world have a striation between the direct labor, which is generally an unskilled workforce, and in many, many countries is regulated by either a national or local labor unions. And all of x86 architecture support is done generally by salaried people and the IT department. And so you had this movement of the process engineers moving into the IT department, or the IT people moving into the process engineering department, and suddenly you're not able to operate with only direct labor. You have to have indirect labor on every shift that you want to operate, because, as we all know, x86 architecture-based stuff needs a lot of care and feeding and support, and there's a lot of parameter changes and things that have to be done that, if you have it in the x86 architecture, can only be done by IT professionals. So that movement created a lot of rediscovery of how to approach the problem, and in fact, it was approached from both ends. The x86 architecture people tried to make their actual devices more hardened for the plant floor, and then there was this whole movement of building interfaces so that you didn't have to be an IT expert to be able to go in and change parameters or make adjustments or make corrections, that you had some kind of lockdown user interface with certain rights that either a production supervisor or other people that are related to direct labor could make the changes. And the PLC people approach it from the other direction of adding more functionality to the PLCs, so that they actually approach some of the compute capability of the x86 devices, to where we arrive today, where you can actually put an x86 device in the PLC rack so that it communicates directly with the PLC. But we have this continuous problem of direct labor versus indirect labor, and the dependencies of production on different departments that, traditionally were not merged, and so the merge and unmerge continues to happen. And then you have the additional problem of licensing across borders, and the movements today of manufacturing are not small movements. They're not from this facility in this country to this facility to another facility in this country, or to a nearby country across one border. They're across large geographical areas. And then you get into, there are diverse requirements between countries for their legal, licensing, and taxation implications for the use of the licenses. And in fact, today, you can use an MPLS network and make everything look virtual, so it's in the same country, but you can't draw licenses across borders without being able to account for the use of those licenses, and you're beholden to the taxation needs of those countries. So it's become very, very complicated.
Oh, interesting. And so you talked a little bit about the technology, right? And for example, how x86 was starting to be incorporated, controllers were getting bigger, how the hardware is changing. But one of the things you also told me about was why these changes were happening. I mean, why do you want a PLC to turn into a PLC? Why do you need more intelligence in your process?
Product genealogy has become more of a standard than a small subsegment of manufacturing. It used to be you had to have a federal motor vehicle requirement that you have product genealogy, or if you were in the defense industry, or there were certain airlines, commercial space, commercial airline space, anything in the defense industry, they all had product genealogy requirements. Well, nowadays, everything has product genealogy requirements because of our litigious society and because of the drive for continuous improvement and being able to localize any problems that you identify and be able to contain them. Product genealogy has become almost universal. So every time you ship a product, plus the electronic transmission requirements, you got to send an ASN that says, here is the product that we just made, and it has to be able to drill down to, on this product, when we inserted this screw, at this moment, the torque on this screw was this. So those kind of requirements have become very, very widespread, and that's given rise to the proliferation of the stuff far beyond what it was 15, 20 years ago.
Interesting. And so in summary, you're saying Processes need to be more flexible because, as you talked about with your anecdote, labor costs, transportation costs, etc., are pretty dynamic, and manufacturing tends to be look for optimal ways of solving cost problems. And so people want to move the location of their manufacturing around. They want to change the types of things they're making frequently because it is discrete manufacturing. And then you're also saying, in addition to the flexibility, that there's an enhanced need for interoperability and transparency across processes.
Exactly.
Okay, interesting. Okay, and so you talked well so far to this next slide, which is how you just explained how the equipment has gone from very specific and easy to troubleshoot to being much more flexible and dynamic based on these requirements that we just talked about. And so probably don't need to talk about that. But my next question would be, so you said, okay, PLCs are evolving. They're getting much bigger. They're turning into x86 devices in many cases. So in a way, x86 is already in the factories, and I'm sure it's already there from the IT side. So why wouldn't you just use a PC to do this kind of work instead of a PAC? I mean, you said of course that direct labor was very expensive, but at the same time, I mean, I could argue that these things are manufactured in huge quantities, right? And the quality is extremely high. I mean, for example, one of our suppliers, the Dell uses Quanta, makes over 50 million laptops a year, right? So we have extremely high quality these days. Things have changed over the last 10 years. Of course, cost is extremely good compared to proprietary or very specialized hardware. And they're so flexible that you should be able to accomplish just about anything you need to do except for, extreme, real-time requirements with sync clocks and that kind of thing. But for everything except the most extreme motion control and that kind of thing, you should be able to accomplish what you need. And the best of all, they're going to be interoperable. So you make a device, use OpenPLC, for example. It works as a PLC, but now you can also use open source libraries. You can use common middleware, messaging queues, and logging, and you gain all of the same infrastructure, and you can leverage all the same software infrastructure that exists for enterprise software, which has many of the same goals of trying to have centralized process control and patch management and these types of things. So you can leverage third-party software, including open source software, which is very useful. And like I said, they're pretty fast nowadays. So can you talk a little bit more about the specific needs of, why couldn't you just create a ladder logic interpreter, and that way you're still keeping the costs pretty low to troubleshoot logic problems, for example, in the system?
That's a good question, and the bottom line answer is that it's not the hardware. And I'm not saying that because I work for Dell. It's not the hardware. It's the overall architecture. Let me give you a real-world example of why a computer system can cause a line to stop. You have material delivered to the line. You scan in the material, and you say, okay, I'm opening a new box of screws. I scan the box, and that scan includes the screw lot number, the screw part number. The lot number of the screws is tied to the engineering change level of the screws. You start putting the screws in. You get halfway down the line, and the ERP system that the product genealogy collection software is communicating with across the MPLS, the ERP system calls back and says, that is the incorrect ECN number, stop. So the line stops. Now, there's no way a direct labor person can go solve that problem. A direct labor person can come out and say, okay, the devices are communicating, the actuators are actuating, the screwdriver is driving the screw. I don't know what to do next. It says the engineering change level is wrong. Call the quality department. You call the quality department. They come out and they say, okay, well, engineering change level, is that engineering change level correct or not? They have an engineering change release from the customer. They approved the engineering change level on the screw raw material, so it should be going through. I don't know why the ERP is saying no. I got to call the IT department. Now I call the IT department. The IT department goes into the ERP and sees that the engineering change level of the screws that were just delivered is not in the list of authorized engineering change levels for that particular raw material. So they call up the actual product, the procurement department, to find out, did you put in the authorization for the new engineering change level? You got the release from IT, you got the release from the quality assurance department, which was based on the release from the customer. Did you actually put that in the procurement system to say that's an authorized? Oh, no, that guy was on vacation last Thursday and he didn't put that in yet. We didn't know the material was going to arrive by this time. So all he's got to do is go into the procurement section of the ERP and say, this engineering change level is correct. So it's this chain of events in the entire architecture that is generally, in our current experience, this is 80% of the production stoppage, is this kind of stuff. And so we found that the best architecture is an architecture that allows the line to keep running, stores the data locally, and then the communication with the rest of the architecture and the communication back to the ERP is able to cache and is able to continue the line and then catch up later. Now, certainly you want to stop the line in some circumstances. You may have a material limit that you want to move from one material value-added activity to another value activity. You don't want it to go over a certain amount before you get the cash back from the ERP. There's all kinds of things to consider in there. So the point of it all is it's a very complicated architecture. It's not the hardware that is the problem. The hardware becomes a problem when you're not able to duplicate the hardware you need as you move around the world. So the point, let me see, the bottom line point is, as a plant manager, I could care less if it's in the PLC or the PC. And I'm sorry to say that as an employee of Dell also, but really, all I want to do is make parts, you know?
Sure. So, but let me ask you this: so, if what you just said was it's a process problem, it didn't seem like it's really a decision between PLC or PC. So why wouldn't you see people, for example, that process problem you just described, wouldn't that exist even if you had no PCs, right? You implemented the whole thing with PLCs. I mean, if you have a system that's going to fail hard when it finds a product or you see a piece of a unit of a screw come in and it's not on your ECN, I mean, that's the right behavior, right? It's not, the system's kind of working as designed, and the problem is it's a process problem, right? The procurement person hasn't authorized this particular part to be used. And so in a way, the system's working exactly as you designed it. So in that case, why wouldn't everything move to PCs? Does that make sense?
Yeah, that does make sense, and you have to leave the data exchange and the algorithm exchange that has to happen between systems has to reside in the PC. So you just have to live with that, and everything other than that you want to move into devices that your direct labor can handle. Direct labor is the cheapest labor. Indirect labor is the most expensive labor. You generally don't staff indirect labor for all of the shifts, all of the hours of coverage that you staff direct labor for. So as a manufacturing person, all you care is I need to be able to run and make my parts with direct labor only. And then if there are limits for how much you can run when the inter-system operations are broken that indirect labor has to fix, then you have to set up those limits. Sometimes those limits are very small, but you want to expand them to the greatest point possible so you can continue to run with just your direct labor.
Interesting. See, what you're saying is the architecture you set up, well, it might make sense from an IT deployment purpose, from a sustainability and maintainability perspective. You got to think about who's maintaining this stuff. And so while it might be really novel and interesting to use distributed computing to centralize all your approved vendor lists and your approved, the products, all the logic and the catalog that says these are approved products to use as inputs into this process. It might be interesting from an IT perspective to centralize that all in an iSQL database, et cetera. The fact is, when you get an exception, and whether it's a person that caused the problem or whatever, but you actually have a supplier now delivering a part that should be authorized, it's very complex to track that down. So you're saying it should be you should consider an approach where an unskilled labor person can easily figure out what the problem is.
Yes, or it immediately tells you that this is a computer problem. Don't try to solve it on the line. And in fact, the real world example that I gave, that company has had to staff IT people in their direct labor.
Sure.
The product genealogy requirements for them are so strong. They make airbags, and so it's controlled both by whatever country's oversight department for explosive devices, as well as federal motor vehicle standards. So their product genealogy and the queues between value-added workstations have to be so small that they ended up just deciding, okay, we moved everything we could into the PLCs, but we're still very, very dependent, even in lots as small as 10, we're very, very dependent on the interoperability of all the different computer systems. So we just staffed it with IT people. We put IT people in the direct labor on every shift. So sometimes you have to do that.
Explain to me again, though, so if you're using a PLC and that turns into a PAC, I mean, I've just taken a browse around some of the program. I mean, it's a full-blown computer, right? You're using object-oriented programming and huge libraries. It seems like it would be very, like you still have the same problem, which is you need a programmer to troubleshoot the issue, even if it's a PAC.
That's right. That's right. Because as you pointed out earlier in our interchange, this stuff works now. 10 years ago, computers would lock up, blue screen to death. You would have that kind of stuff. That doesn't happen anymore. You put the right operating system on, and you build the software right. The stuff can run 99.49s. You can have backup devices. You can have failover compute devices. All that kind of stuff, that just works. Now it's down to the interoperability of all the different systems.
Interesting. And so let me ask you this: do you guys, when you do use PCs in your architectures, what kind of PCs do you use? Do you use expensive ones or just off-the-shelf Dell products, or what do you use?
We use the cheapest PCs we can get, oftentimes used from deployments of new desktops and laptops to people in the office, and we take the old ones and put them out there, because generally you're running some version of Linux. It doesn't require a lot of hardware, and you're writing very, very simple architecture screens for interaction. All it's doing is taking some interaction, taking some data, moving it along to the big compute systems. So what we generally want is the cheapest thing possible, and a closet full of spares, by the way, because when the PC does fail, the direct labor is not going to figure out that, oh, it was the hard drive. Oh, it was the hard drive cable. Oh, no, it was one of the memory sticks. No, they don't have time for that. You're going to whip it off the line, whip the new one on, keep going. So we want the cheapest ones possible, and we have to have the exact same architecture, physical architecture, of the ones we swap out. So if I have three $3,000 data capture cards and they're ISA, I need a closet full of them.
Yep. So that makes sense, and that's exactly what I expected, which was you're saying all the mission critical and even the really important stuff is done by the PLC or PAC, and then you just use a small glue layer of cheap PCs to do any interoperability you need.
Exactly.
Is that right? Okay. And so yeah, so then, but see, I still come back to the crux of the issue I see, which is PACs, PLCs, well, I'm sure they've gotten more cost competitive. Still, they're extremely expensive devices. So it would seem to make sense with what you're saying to use an off-the-shelf, a cheap PC like you just talked about, but even use it up front as a critical piece of your components or your architecture, and just use software to try and isolate when things are going to fail. Here's how they're going to fail, just normal use cases and behavior models for your product, and make sure okay, if it's important that this thing is easy to troubleshoot and the logic is in one place, fine, make a ladder logic, use a ladder logic interpretation engine, and do all your customization in very simple ladder logic. If it's important that you're able to troubleshoot an approved vendor list problem. Well, fine. Make a simple approved vendor list right there in that same, the same place where you're going to see a failure. If there's a supply issue like that, put a very simple, a text file with the approved vendor list in it, so somebody can troubleshoot it right on the spot. So why wouldn't you just say, look, take all the value out of the hardware and put it into the software and use these cheap PCs?
That's the right answer for a lot of the parameters. And the most cutting-edge companies that we deal with right now that are moving manufacturing regularly and changing over their lines regularly, they put as much as in the PC as they can, and they cache locally. As you pointed out, you can cache some of the stuff from the ERP in a local intermediate, almost like an ERP junior, so that even if your MPL, another problem, the MPLS goes down, especially if you're in Romania or you're in Mexico. I mean, these things happen more frequently there than they do in some other countries. If you lose communication with the ERP system, that can cause a line to stop too. Well, you can cache a lot of information locally in an SQL database or Oracle database any other way, and that'll keep the line running. But there are a lot of parameters that you would never want to move into a PC. Let me give you a specific example. You're running a line, you're driving a screw. The person that drives the screw, an industrial screwdriver generally has a torque feedback setting. The screwdriver actually has a voltage, and it has to get a signal to say, use this much voltage because the expected torque outcome is likely from this voltage. And as it drives down, there's a stop pin, and when the stop pin hits the surface of what you're driving the screw into, it makes it connect, it makes electrical connect, and it tells it to stop. So you're likely, because of the voltage and the position, you are likely at the correct torque. Now there's a load unit inside the screwdriver also that reads the torque. So all these things happen at once. Now, what happens when your screwdriver drives down and it's got the right voltage, it hits the right position, and the torque readout is wrong? How do you solve that problem? That's not a software problem. You call your maintenance guy. Likely what's happening is the brushes on the motor inside the screwdriver are worn out, or the motor itself is just starting to burn out, so the screwdriver needs to be replaced. Well, how do you know that? The maintenance guy comes over, he takes a test device, he drives it down, he has to look in the ladder logic and see, okay, I received the stop signal, or what if I didn't receive the stop signal? The pin hit the surface of what you're driving the screw into, and it didn't read back the stop signal. That means that the wire that goes from the capture card to the actual screwdriver has a break in it somewhere. Or maybe the resistance in the wire has built up, and it's getting the signal of stop, but the signal is at too low a millivoltage, and so it waits until it goes a little farther and the millivoltage actually starts to rise before it recognizes it. That's the real world kind of stuff that happens, and it takes a maintenance guy to fix it. Your IT guy can't fix that. So you want that in the PLC. So that's to answer your question. You can't move everything out of the PLC. You cannot do it.
Well, but I still would object. I'd say there, all you're saying the things you need to make sure that the problem is easy to troubleshoot is that it's ladder logic, and so the person can inspect it and do a trace through it and easily figure out where the logic is not acting appropriately or where something's acting strangely, and then because they use that ladder logic, they can, and it's easy to figure out that they can go, well, it looks like it's probably a problem with this wire. So what's the difference between whether that device is a PLC interpreting ladder logic and connected to a wire, or it's a PC that's doing the same thing?
You're right, because you can display the PC. You can display on the PC with the same type of view, the same simplified view as ladder logic. You're absolutely correct. It has to do with the different skill sets, because the direct labor maintenance skill set doesn't know how to go into the software. He doesn't know Linux. He doesn't know whatever Apache server, front end, web view. He doesn't know how to go in there to find the stuff. You can display it in a ladder logic view to him, but then that's a display. Now, how does he step it through? Can you duplicate the PLC? You can actually put an offline PLC control device in your hand, plug it into the PLC, and step through the functions. Ladder logic step at a time or a partial logic step at a time, and actually see what's happening. So you're you're a physical mechanic standing there doing this. You can duplicate that in the PC too, but what happens if the PC is interpreting it wrong? You know, there's just so many layers of algorithms, so many layers of interpretation. You want to get as close to the device as you can. And even after the maintenance guy gets the, whether he gets it from a PC or a PLC ladder logic view, identified that it's probably in the cable, he ends up taking the cable off of both ends and putting a voltmeter on it. And now your IT guy can't do that. You need a maintenance guy to do that. And then he's going to go rebuild the motor. So you can move, it's a gray area, as you pointed out, and you can move the barrier of this gray area wherever you want. And what we find is that the optimal position of the gray area barrier is you have skilled trades, you have direct labor, keep the barrier in a traditional position, and in some cases you have to move it. Like I said, sometimes we have to occupy direct labor with IT people, but you want to keep it to the lowest cost labor. That's where you want the barrier.
Very interesting. Okay, so
let me just ask a question. There's a lot of questions we're getting about reliability of PCs, both from a hardware and a software standpoint. And of the questions we're getting, that seems to be a big concern. Can you address attacking that? The view that the PLC is more reliable than the PC.
Yeah, I can speak to it. Tim, do you have anything to say about that?
I'd like to hear your answer.
Okay, so I would say, we all owned a Windows 95 PC, and we of course were not that impressed with it. The same thing for Windows 3.1. But I would say that things have changed quite a bit about reliability as far as PCs are concerned. Now, what I also would say is I will not, by any stretch of the imagination, purport to say that a PC is always, any PC you buy from any vendor, even a Tier 1 vendor, is going to be suitable for 24/7 operation. And it's going to be possibly have the same reliability that maybe some really expensive, highly or robust and well-designed PLCs might have. And what I can say is, as I said before, the quality that goes into a commercial PC today is extremely high, and it has to be, because when you're producing tens of millions of PCs a year, the price Dell would pay if we don't meet our specified quality thresholds, just in warranty costs, will be enormous, and we'll get destroyed by Wall Street, right? So just like we had we've had a couple well-publicized quality issues, you can see what happens when Dell has a quality slip, right? And it's extremely visible, it's extremely painful. All of our customers pay a price. So in a way, by going to high-volume commoditized hardware, you're actually gaining much higher system quality, because it has to be. That's the only way we can run a lower margin business, because we can't be eaten alive by our quality problems. That said, the problem you will normally find is most PCs from Dell and HP and Acer and IBM, they're all made for business environments. And so sure, we may say they'll last, or we may know they'll last for 3 years when you operate them 8 hours a day and they're in a nice air-conditioned environment. And in fact, that's why one of the reasons Dell OEM Solutions exists, because we've made, for example, we've made an industrial PC. Dell's the only Tier 1 vendor with an industrial PC, and we've made a PC because our customers who resell our products as their own. So these would be, as an example, and I'm not saying this happens today, but as an example, we could Siemens could be reselling our PC with their name on it, right? So we put PCs into MRI machines, we put PCs into ATM machines. These are all people with similar requirements. There are already people running these products in factories because they're designed for factories. So we've designed a specialty product specifically for these needs. So I would argue, while highly proprietary and customized hardware, including PC-based hardware, there's no way you can guarantee the quality of those types of products. I mean, when you're producing batches of 10,000, how do you statistically guarantee quality? And yet, because of interesting offerings that Dell has, and I'm sure other people are considering, Tier 1 PC vendors are now starting to address these specialty markets So you can now get the quality and even the tech support that you would need to maintain the reliability of a product based on a Tier 1 PC, and yet it's designed to function in a more rugged environment with different operating temperatures and round-the-clock operation.
What about redundancy on the hardware level? Because that's a question that's been coming up on from people from the audience.
Yeah, well, that's a great question. So, there's two ways to look at that. One is, and I think I see where this person's going, is, there are many design patterns for addressing reliability in x86 architectures and really in any architecture, but how people do it with low-cost hardware, and redundancy is one of those. And there's absolutely no reason that you can't use a software interface and provide some redundancy at key points in your architecture that are critical to ensure that even if the worst does happen and you do have a failure, that there still is another device there to take its place, right? Or even load balance if you need dynamic capacity. So I would say the way people provide reliability in hardware, if normal Tier 1 PC servers and commercial desktops aren't enough, is using redundancy with interfaces, rather than trying to design a single piece of hardware that just can't ever fail, because that's a pretty high standard to live up to.
That's very true. The other side of it that we're getting a lot of questions on is the operating systems. And I heard Linux mentioned as one option in some applications, but that is a big fear of people that have used PLCs, that they have a real-time solid operating system versus what you'd run on a PC platform.
Sure.
Can you want to comment on what you're seeing as new?
Yeah, I've seen a couple trends. Of course, we do qualify it. Well, I should say this another way. The Dell OEM group can allow you to install any software you'd like using our factory. So if our options do not meet your needs, you can always still use our factory infrastructure to install your software and make sure that the boxes for your deployments, if you're working for Ford and you're a manufacturer, an integrator, or you're providing some automation services, you could buy our industrial PC, we can install your custom hardware, we can install your custom software for you, and we can deliver it globally on your behalf with your name on it if we want. And it'll have all the FCC regs, etc., for a global distribution. But that said, I'm sorry, Bill, Bob, what was the question there?
Well, about the real-time operating.
Oh, real-time operating system. That's right. So for real-time, we do have customers that are currently qualifying, for example, Green Hills for a hypervisor, which is a real-time hypervisor that I'm sure everyone's seen at a trade show. You may even be using it today. And that is one approach we're seeing from certain customers who do need real-time performances. Using a real-time hypervisor, you can then run, of course, an RTOS next to the HMI, right, of a system.
Okay.
And may I chime in on the last two questions also?
Yes, please.
I liken the entire compute world, the status of it, to about 1925 in the automobile world. You had to fix your own car back then. And when cars first came out, they came with a manual that showed you how to take the entire thing apart and replicate any single part because, frankly, you had to do it. And someday, the compute world will be truly an appliance. And, that's the whole view of the industry, is we have to get to the point where PCs and similar compute devices are appliances. When was the last time you had to reboot your refrigerator? PLCs are thousands of times more reliable than PCs, plain and simple. We have PLCs in the field that have been running for 20 years, 10,000 actuations a minute, and they still run great. You can go to a box full of old PLC parts that have been sitting around collecting dust for 5 years after they've been in service for 10 years, pull one out, stick it in, and it'll still work. PCs are so far from that, and they'll get there, but they are still far, far from that, including the operating systems. The operating systems spend most of their time keeping themselves running and very little time actually doing what you're asking them to do. So I know that's a little contrast to what you said, Josh, but to my original point of you want to keep as much of the production in the hardened PLCs as you can, and the PCs are almost like, you know, the evil thing, and you put as little as you need to in there, but you have to have them because of all these engineering algorithms and product genealogy. You absolutely have to have them. There's a lot of interaction with the ERPs, so you have to live with them. You want the most reliable ones possible.
That's actually a great point, because you know what you just pointed out was, you know, I talk to the hardware because I do tend to be a hardware specific person in the PC world, but you're right. When a system is general purpose and inherently complex, because it can handle many different tasks, it is of course going to be less reliable because there's more things that can go wrong with it. And so that's a really good point about the appropriateness of PLC versus PC, reliability, and how we talk about those things. And the other one I wanted to point out is you know, when you say life cycle, for normal Tier 1 hardware, a life cycle is, oh, you can buy it for 12 months to 18 months, right? And you can even get it with a 3-year warranty. And you just mentioned, you know, 15-year requirements. So one thing we have done, and I want to talk about that for life cycle, one thing we've done to respond, and I just want everybody to know that there are options out there, right, for Tier 1 PCs. Is, I won't say we'll go to 20 years, but a lot of people can't deal with 1 year. And so what we've done is we've created, with our industrial PC, for example, we've fixed components and provided an optional 5-year warranty. And I know 5 years sounds low, but maybe if we can figure out the right way to use PCs to take over more of this proprietary functionality, but not absolutely all of it, you can still gain some extreme cost advantage by, you know, by using a product, deploying it for 5, and then upgrading it, right, every 5. It's a way to at least bridge the needs, compromise, if you will, so that you're not having to deal with extreme change, but now you can deal with a little more change every 5 years and gain some good cost advantage. So that's probably a good move to this next slide, right? Which is you know, we've talked about a few things, right? And I can pull out of my hat some solutions to a few of them, at least in my mind, which is challenging environments. We've got a Tier 1 PC that can address that need. It can run in you know, a factory environment around the clock. For customization and support, you've obviously pointed out that you've got to get a system up and running. We have global tech support. We can provide SLAs of hours for hardware replacement, and that's global. And we can customize using our infrastructure. We've got a little bit longer life cycle, so that it allows you to move on to at least a Tier 1 product. But at the same time, you pointed out that inherently a PC is going to be complex, and it's not going to meet 100% of the needs of a PLC, and of course the performance is extreme as well in many cases. That you can't guarantee that kind of performance without, you know, very special operating systems. Is that accurate? Tim, do you think that accurately summarizes the situation? Tim, are you there?
I wonder if we lost Tim.
No, we didn't. I'm sorry.
Oh, okay.
Can you hear me?
Yep.
Yes, we can hear you now.
Okay, I lost the last half a sentence. Must have handed it back to me.
Yeah, well, I just asked you if that kind of summarizes. This is my interpretation of what we just heard, which is, while there are Tier 1 PC options that can address some of the needs of why you would choose a PLC, there are still certain particular and important requirements, like the complexity, low complexity, that a PC, of course, just can't address.
Yes, exactly. And the audience, I hope the audience appreciaes the fact that we're having a live debate between members of the same company here. This is the exact same debate we had when we were invited to do this webinar, and we came on with not differing viewpoints, but viewpoints from totally different approaches. And we've opened our kimono and had the debate as openly as possible in front of everybody.
Good. That's when my gut instinct is, you said, the number one requirement of why you would use a PLC is, of course, extreme reliability with no single point of failure, because you have a single point of failure, in many cases. You want it to be extremely reliable. You need it to be extremely performant. And then the secondary requirement is now, because you've met this is the right device for this situation, it also has to be extremely easy to troubleshoot because of labor costs. So you got to keep it simple. So my question would be, and you probably have seen this coming, but it's, okay, instead of moving down the PAC road, it seems to me that a PAC is I don't want to say the worst of both worlds, but you're compromising what's so important about the PLC or the embedded controller in order to get flexibility. Why wouldn't you move that gray area, as you call it, closer to the PLC, right? And so you say, okay, a line 10 years ago looked a little more simplistic than it does today. Why wouldn't you use that same line and then draw that line, or then deploy a PC next to that controller and take over a little bit more of that responsibility, right? In fact, I would even argue, why not handle as much in the PC as possible, except for those extreme components where you do need extreme reliability and you need extreme simplicity, right? And you architect your system that way. You say, here's the logic that could break, here's the hard failures we could have. These all need to be easily diagnosable in PLCs. Okay, now all the interoperability, all the logging, all the genealogy tracking, this kind of thing, that of course needs to be done on the PC side. Right? So in other words, kind of treat the PC as more of a first-class citizen in the environment versus, oh, we've gotten to the limits of a PAC, we have to use a PC, and that's all that a PC is going to do. Because it seems like a PAC is compromising the whole point of the PLC.
Exactly.
Okay.
You know, this is Bill, and I must say, when we first had this discussion, I was intrigued by this thought of using a simple controller with the computer, because computers have changed so dramatically. It was something I'm a veteran of the industry, just hadn't been thinking about, because we just keep jamming more into a controller today. So I think it's an intriguing concept, a little different than what our current line of thinking has been. Certainly there's some positives and negatives along on the balance sheet for this, but it is intriguing. Tim, what is your thought on this?
Well, I think you brought up a good point that we hadn't really addressed yet, is that another side of the movement was to push more and more of the engineering algorithms and the inter-system communication into the PLC, and that doesn't work well either. We've discovered over time, because it becomes harder then to diagnose the inter-system communication problems, because the PLC maintenance guy actually is the first line of that then, and he discovers the communication problem and he has to hand it off. You're much better off keeping the gray line, as Josh pointed out, clean between the things that need to actuate on the machine need to be in the PLC, and the inter-system communications needs to be in the PCs.
Interesting. Well, we've got a lot of different questions, and I kind of touched on some of them already. A lot of it has to do with, we've talked about the life cycle. I think that is an issue. And software management, because typically with PCs, when you put them in a plant, the IT group gets in doing things like remote patch management and things that can create problems in the stability of a production environment. Is there any comment on, I guess that's management maybe, but Tim, maybe you have experience with this.
Oh yeah, I could tell you, in the same facility where we have very close, where the PCs are very close to the equipment, and in the same facility a couple other lines are entirely PLC driven, I can tell you that when we had worldwide virus outbreaks, the ones that were PLC driven continued to run.
Okay.
Yeah, that's a great point.
You know, that's been true up until the latest virus, but the Stuxnet, if you've read about that.
Yep.
Yeah, I mean, that's something, Bill, you brought up on a phone call a while ago, which was, and I'm not sure what your thoughts are on this, Tim, but my thoughts are, this is again a symptom of treating a PC as glue and a second-class citizen in the environment. Right? And Stuxnet's probably a good example, right? Which is, is, okay, if you're using a PC to check your email and to possibly upload some ladder logic changes to your controller if needed, but it's really playing a very secondary class role, then in many ways it doesn't get the same respect that a vital piece of your infrastructure does. And so, if you leave Windows file sharing on and you leave all the USB ports turned on, that's just irresponsible in a lot of ways. And I know you could argue, well, it's a lot of complexity to manage, et cetera, but I mean, we run the Department of Defense, right? We have financial clients with extremely valuable data, right? And we have created solutions to allow them to address those security concerns. Let me give you an example. Our product group has come out with a piece of software that will work on any PC, but it will allow you to essentially micromanage all of the I/O of the system, so that you can go from encrypting what's on the hard disk to making sure you turn off all your USB ports and who has access to various features of the product or of your hardware, and the interoperability of it, and the ability for people to get into it and infect your systems. So assuming you got your hardware segmented on the network correctly, you can easily use this software that we've developed on your behalf, and it'll work on any PC, to create a policy that will work correctly for your security requirements. Right? Now, if you're going to use a PAC or a PLC, it's really up to you to figure out how that works, because they're very, you can say they're obscured and they're secure for that reason, but there are very well-defined interfaces, and it's kind of up to you about how you're going to use them in your architecture, and that's what you get, right? Versus using a PC, which of course it's general purpose, but we've created specialty solutions that you get to leverage because you're using a PC to lock it down. Right? So my argument would almost be, especially if your security strategy is 100% to not be connected or to be obscure, the world is getting more and more connected every day. Right? Everybody walks around with USB keys. They walk around. Stuxnet's a great example. Maybe 10 years ago you could assume that somebody's not going to do anything crazy to your network, but now everybody's carrying around iPhones and everything's networked. If you want to get really sophisticated, there are a lot of points of attack. So trying to say my solution is impervious because it's just not connected, that's not going to work. Right? You've got to now design your solution. Sorry, go ahead.
Unfortunately, we're running out of time.
Oh, sorry.
I hate to say it.
Sure.
So I just want to remind people that when you exit the window, you'll get a survey as you go out of the webinar, and we'd please like you to fill that out. We'll take the questions that were asked, and we will compile them, and we'll get back to people with answers on issues. There were a lot of questions. So I think we have, I don't know if this automatically will kill us in 23 seconds, but we're pretty close to the end. So,
well, thank you very much, Bill.
Thank everybody for attending.
And thanks, Tim, for attending.
Thank you, Tim and Josh.